Welcome class, myself Professor D.S. Rai, Professor Department of Civil Engineering, BBD ITM Lucknow. Today we will take up course KCE 064 Foundation Engineering, in which we will cover today lecture 38, Design of Wall with Reinforced Backfill. References I have taken Dr. B.C. Punamiya, Soil Mechanics and Foundation, V.N.S. Murthy, Soil Mechanics and Foundation Engineering, Alam Singh, Soil Mechanics and Foundation Engineering, and some material have been taken from the internet. The contents that we will cover today are design consideration, wall with reinforced backfill, illustrative example. So, first of all we go for a design procedure, wall with reinforced backfill. The given data will be height of the wall h, uniformly distributed load q, line surcharge q with its distance from top of the wall face, that is x, inclination of wall back with the vertical beta, density of backfill gamma, angle of internal friction of soil phi, wall friction angle delta, coefficient of sliding for foundation soil interface, that is mu, factor of safety against sliding, that is Fs, factor of safety against sliding F0, allowable bearing pressure of foundation soil, that is Qa, and a reinforced characteristic. We will discuss that is a step 1. So, here select suitable reinforcement, its spacing. This is the horizontal spacing SH and this is the vertical spacing SV. The length is L and width, that is W, and friction coefficient of soil remaining F star. Then we will calculate dP value. By this formula we can say dP will be equal to W into F star H divided by SH into SV. So, by this formula we can find the value of dP. If the reinforcement is provided in the form of sheet, net or mat, then the dP will be F star H by SV. So, there is a notes that thickness of the compacted layer should be considered while selecting the vertical spacing SV of reinforcement. There is no widely accepted criteria for the ratio of SH and SV. The value of SH may be taken equal to SV. For sheet, net, mat type reinforcement, the value of SH as such will not come in computation and it will be unity as design is done considering unit length of wall. The second note is, if the type of reinforcement is not limiting, then wall can be designed by the selecting suitable value of dP and L by H ratio. Now, a number of alternatives can be considered and most economical one can be adopted for execution. However, as mentioned earlier, dP should be equal to 1 and L by H should equal to 0.6. This may give a economical design. So, now we go for the second step. Then we have to calculate by this formula q by gamma h, q by 1 by 2 gamma h square, x by h and L by h. So, we have to calculate this value. The third step will be design against sliding failure. So, in the first, read the value of P t divided by 1 by 2 gamma h square for the value of q by gamma h, q by 1 by 2 gamma h square, x by h, phi and beta for relevant plot. This is a plot, this is a Pt in the vertical axis, Pt by gamma by 2 h square on the vertical axis, and on a horizontal axis, that is q e divided by gamma h. So, this is the plot for a different value of phi, phi is equal to 25 degree, phi is equal to 30 degree, phi is equal to 35 degree and phi is equal to 40 degree, and the corresponding vertical axis, this is the 0.25 to 1.25, where beta is equal to 0. The next step will be using a figure, often the equivalent uniformity distributed load Q e by gamma h dp and L by h determine P by 1 by 2 gamma h square from a different charts or figure given in the standard books. The next is to calculate the total resultant pressure P for a given value of gamma and h. Then E, calculate horizontal and vertical component of earth pressure, where pH, coefficient of horizontal earth pressure, that is P cos delta plus beta, and vertical PV is equal to P sin delta plus beta. F, now select a suitable wall section which can resist the lateral thrust obtained in step 3E with the desired factor of safety. We have already calculated in 3. So, the next step will be step 4, in which we design the structure against overturning failure. So, here also we first calculate the determine the value of MT by half gamma HQ for a given value of the given value of Q by gamma H, Q by half gamma H square, X by H, phi and beta from different figure 67A to 67B. Now, the next step will be using figure 68B, obtain the value of equivalent uniformity distributed load Q E by gamma H for the value MT by 1 by 2 gamma HQ. The next will be C for the value of QE by gamma H, gamma dP and L by H. Now, determine M by half gamma HQ and P half gamma H square using the relevant plot figure 65A and 65P. The next will be calculate H bar to the H, that will be M by half gamma HQ and P by half gamma H square cos delta and sec beta. The value H bar is the height of the point of application of resultant pressure from the base of the wall. The next will be E. Now calculate the value of total resultant pressure P and height of its point of application of H bar for a given value of H. The next will be calculation of horizontal and vertical component of resultant pressure as P H will be equal to P cos delta plus beta and P V will be equal to P sin delta plus beta. The next will be G, find factor of safety against the overturning of the wall section adopted in step 3. If the calculated factor of safety is greater than or equal to the desired factor of safety, the section is OK. If it is less than the desired, try another section of wall and adopt a section which gives the desired factor of safety against the overturning. The next step is step 5. Here we check against bearing failure. The first A is determine the distance x bar of point of application of resultant force at the base from the toe of the wall. Here x bar will be net moment about the toe of the wall divided by total vertical forces V. Now calculate eccentricity E. E will be equal to E by 2 minus x bar. It must be less than B by 6, where B is equal to width of the base of wall base. Now calculate the maximum and minimum pressure intensity under the toe and the heel of the wall. So sigma max, here is the sigma max, that will be equal to V divided by B into 1 plus 6 E eccentricity B base of the wall, and sigma minimum will be B by B 1 minus 6 E by B. So by this formula we can calculate the maximum and minimum pressure intensity. Now if sigma max is less than sigma A and sigma minimum is more than 0, the wall section is OK. If it is not, so repeat the above step till a section is obtained which satisfy the above conditions. The next is to calculate the maximum and minimum pressure. Again we have already calculated. The next step is step 6, design against the tension failure of the reinforcement. So first of all, A, tension, approximate maximum tension of the strip is calculated by assuming that the total net pressure coming on the wall is assumed to be a Rankine distribution of pressure, where K will be equal to K A minus K R, where K is equal to revised earth pressure coefficient K A P T by half gamma H square, where L by H is equal to 0. K R is equal to P T divided by half gamma H square for reinforced fill. So tension T will be equal to K gamma V S H into S V, where gamma V is the pressure intensity at a strip level, and that will be equal to gamma H Q E. where the height I is the height of fill on the strip. T will be the maximum when H I will be equal to H. For the satisfactory design, T should be less than the tensile strength of the reinforcement. So, we go for step 7 for design. For the construction technique, the wall is built as per design dimension. Second, the backfill is laid in a layer and compacted to the desired density till the height of first reinforcement layer is reached. Next is the reinforcement is laid on the horizontal fill prepared at the selected horizontal spacing in case a strip are used. And D, step B and C are repeated till the full height of backfill is achieved behind the wall. Now, this is the design procedure, and for detail we will discuss a illustrative example. Here the design a 8-meter height wall with the inclined back retaining horizontal backfill carrying a uniformly distributed surcharge load of 30 kilonewton per meter square and a line load surcharge of 60 kilonewton per meter at a distance of 3 meter from the wall. The inclination of wall back is 10 degree with the vertical, and other data are like this way. Unit weight of backfill soil is 16 kilonewton per meter cube, angle of internal friction 30 degree, angle of wall friction 20 degree, cohesion 0, coefficient of sliding for foundation soil interface that will be 0.50. The allowable bearing pressure of the soil is 300 kilonewton per cubic meter. The factor of safety against sliding 1.5, factor of safety against overturning is 2, and unit weight of masonry 22 kilonewton per cubic meter. Sorry. Now, come to the solution. The data are given here. Case 1, reinforcement as a strip of galvanized steel. First step, the width of a strip W 30 meter, length of a strip 4.8 meter, vertical spacing 0.4, horizontal spacing 0.4, coefficient friction coefficient F star is equal to 0.4, allowable tensile strength of a strip 8 kilonewton per meter. So, we can calculate the dP by the formula. So, we will finally get 0.6. Step 2, we can calculate Q by gamma H and we can get 0.234, where Q by half gamma H square will be 0.117, x by H, that is x is equal to 3 meter. So, x by H is equal to 0.375 meter. So, now we go for step 3, design against a sliding failure. So, we can calculate here P T divided by half gamma H square, that will come 0.6129 from the figure. Now, the B equivalent uniformity distributed load Q by gamma Q E by gamma H, that will be 0.31 from the figure 6.8. Now, the C P by gamma half gamma H square, that will come 0.301 from the figure 6.4b. P will be equal to 0.3 301 into 0.5 into 16 into 8 into 8, that will come 154.1 kilonewton. Now, the pH, P cos delta plus beta will be equal to 154.1 cos 20 degree in plus 10 degree, that will come 133.5 kilo Newton. Now, PV will be equal to P sin delta plus beta, again 154.1 sin 20 plus 10. So, that will come 77.1 kilonewton. Okay. So, now assume the section of wall as shown in figure 6.2.1. W1 is 124.1 kilonewton and W2 52.8 kilonewton. For a factor of safety 1.5 against sliding, we can calculate this value as, so W3 will come 146.5 kilonewton. Now, calculate B1, that will be 14.65 into 2 divided by 22 into 8, that will come 1.7 meter. So, W3 will be equal to 149.6 kilonewton and V dash will be 3.41 meter. Now, step 4, design against overturning failure. Here MT by half gamma HQ will be equal to 0.2479 from figure 671. Equivalent uniformity distributed load QE by gamma H, that will be equal to 0.33 from the figure 68B. So, the value of QE by gamma H will be 0.33. So, now M by half gamma H cube, that will be 0.05 from the figure 65 K, and P by half gamma H square 0.309 from figure 651. D H bar by H will be 0.15 divided by 0.309 into cos theta cos 20 degree into sec 10 degree, that will come 0.509. So, H bar will be 0.509 into 8, that will be 4.072 meter. Is it? So, now calculate P, that will be 0.309 multiplied by 0.5 multiplied by 16 multiplied by 8 square, that will be 158.2 kilonewton. And from this pH we can calculate by P cos delta plus beta, that is 158.2 cos 20 plus 10, that will be 137 kilonewton, where PV P sin delta plus beta, that will be 158.2 sin 20 degree plus 10 degree, that will be 79.1 kilonewton. Now, factor of safety of wall section from step 3F against overturning, that will be F0 will we can calculate by this formula. So, it is coming 1.54 meter. So, eccentricity sorry 13 equal to 13.22.4 divided by 557.6, that will come 2.38, which is more than 2, hence it is SF. Now, come to the step 5, check against the bearing failure, determine the x bar of the point of action of resultant force at the base from the toe. So, x bar we can calculate, that is coming 1.54. So, eccentricity is 0.69. So, B dash by 6 is equal to 0.74. So, E will be less than B dash by 6. So, we can calculate here sigma maximum V by B into 1 plus 6 E by B. So, it is coming 215.6 kilo Newton per meter square, which is less than 300 kilo Newton. So, it is SF. So, sigma minimum again 497.1 divided by 4.45, 1 plus 6.69 divided by 4.45. So, it is coming 7.8 kilonewton per meter square, which is more than 0, hence it is a safe. So, a wall section of 4.5 meter base width and 0.3 meter top can be used. The section of the wall has shown the below. The volume of wall is 19 cubic meter. So, now come to the section 6, step 6, design against the tension failure of the reinforcement. Here we can calculate K, Ka minus Kr, and that is coming 0.3119. So, tension T will be 7.88 kilonewton per strip. It is less than 8 kilonewton per meter, hence it is a safe. So, design of wall having the unreinforced backfill gives the section as 6-2B. So, this is the section we have. This is the point of application of the load from 3 meter from the top, that is the 60 kilonewton, and this is the 30 kilonewton per meter line load, 8 meter height, and the different loads are given here. So, this is the wall with the backfill reinforced by galvanized steel strip. This is also the volume is 30 cubic meter, and this is the dimension we have already find with the unreinforced brick. If we are not using any reinforcement, then the section will be this one. So, that is the hint. Thank you very much. Thank you.